Okay, hello everybody. It is my great pleasure to welcome Bram Mesland as our next speaker. He will tell us everything and more about principal equivariant spectral triples, which is one of our work packages. Bram, the Zoom is yours. Take it away.
Thank you very much. I hope everybody can see and hear me. Yes, so this is a talk for this midterm meeting in which I will report on some of the progress in this work package. Let me, yeah, so this is working. So this project was designed from some joint work that I did with Brani Merkacic now some years ago already, which was about non-commutative principal bundles in the context of spectral triples, non-commutative differential geometry. So I will do a quick recap of that work because it's motivational for what is to come, but also not all the aspects of that initial abstract work will be covered after the first 4 slides. So the first 4 slides here are really just a recap of the motivational aspect of this talk, and then I will actually move on to some graph C-star algebraic direction that part of this project has taken. So I think that will be very fitting. So let us first recall principal bundles in geometry and physics. So given a compact Lie group G and a compact G space, all very simple, no non-compactness, where G acts freely and properly and has a nice quotient B, then this is the classical notion of a principal bundle. And on the level of the commutative C-star algebras, we have the function algebra on P, and that on the quotient can be identified with the fixed point algebra of the corresponding action on the C-star algebra. Now, let us assume that we are in a smooth setting, so that the projection map from pi to B is a smooth Riemannian submersion.
Sorry, Bram, I cannot resist it. If you say that P is a compact G space, isn't it, and G acts freely, isn't it automatic that it acts properly?
Sure, yes. If everything is compact, then that is automatic.
Sorry, I couldn't resist.
That's all right. And we get the wrong way map in K-theory from this submersion. And there's an induced class. Now, I will also say that already for these last 2 points, I can say that in the new work I will be presenting, we have not been able to make contact with that particular aspect. But there is work in progress and future projects, of course. So long ago, Elwood made sense of what a principal action should be in the context of C-star algebras. This is also something that will not really come back in the sequel. An action is principal if the map defined on A tensor A into the functions from G to A, given by basically the action and the multiplication, has dense range. And this is an if and only if in a commutative case. So CP is a principal G algebra if and only if G acts freely on P. And now the comment of Piotr is relevant. If everything is compact, then the properness is automatic. So these principal G algebras give a notion of topological principal bundles, and with Branimir we extended this to a smooth setting of G spectral triples. So let me give that definition, although I think most of you in this audience are familiar with that. A G spectral triple is the following data. So we have an algebra, a Hilbert space, and an operator, where here in the most general setting, the Hilbert space is graded. Again, today I will only be talking about odd examples, so there is no grading. D is an operator of this form, which is G invariant. So actually, I should have put domains here because D is an unbounded operator, but it acts in H and it goes from H plus to H minus, and the resolvent is compact. And so the action of G on H should commute with this D. And then there is a dense subalgebra of a C-star algebra A that acts on H in such a way that the representation is covariant, which means that so A is a G algebra, and the conjugation by the action of G on H should implement the action of G on A. And then the commutators are supposed to be bounded. So this is the very common definition of a G spectral triple with a compact structure group. And given such a G spectral triple, we can form what you could call the fixed point spectral triple. And the inclusion map from the fixed points into A can then be viewed as the analog of the bundle projection. Okay, so, well, given a spectral triple, there is a canonical module of 1 forms given by these expressions. So this is a subspace of B of H. And you can look at inner product modules over the smooth algebra and the C-star algebra and connections thereon. And then you can, the analog of topological principal bundle, you can smoothify that by requiring that there exists a bimodule from A to the fixed point algebra with some other unbounded operator and a connection such that we have this kind of tensor product decomposition of the big spectral triple AH0 D0 relative to the smaller one BH1 D1 and this bimodule. And that's a smooth version of a factorization in KK theory. And with Branimir, we established that under certain conditions, any G spectral triple can be factored in this smooth way.
Sorry, a silly question.
Yeah.
Could you go back? Yeah, so this omega-1d, is it just a module or a bimodule?
It's a bimodule, of course.
Okay,
so,
because it says module, okay.
Yeah, well, it's supposed to be bimodule. So,
Okay.
of course, the left module structure is obvious from the way I've defined it. And
yeah.
for the right module, you need to do an inverse Leibniz rule, and then you see that.
Exactly, this is what I expected. Okay, thank you.
No problem. Okay, so the motivational result for this work package was that we proved that given an equivariant spectral triple, of course, satisfying a mild list of further conditions that I'm not stating this time, since I did it in the first talk 2 years ago, there exists a bimodule and an operator and a connection such that this actually factors. Okay, so this was an abstract result that was, yeah, very motivating. But of course, we worked with classical groups here, which I will still be doing today. And of course, the question is, there are commutative examples. We could also deal with classes of theta deformations. But what one would really like to do is also consider the case where G could be a quantum group. This is still rather far away, but also there is a demand for more examples. And that's what the rest of this talk will actually be about. Examples coming from graph algebras. So in order to motivate that a little further, let us first focus a little bit on this notion of equivariant spectral triple, where the structure group G was required to map or to commute with the abstract Dirac operator. And in a manifold case, we have the following characterization of such maps. So if I have a compact Riemannian manifold, so M and G is a Riemannian metric, and I have some diffeomorphism, then that diffeomorphism is an isometry for the metric if and only if the automorphism it induces, which I will, for precision, denote with gamma upper star, so the automorphism of the smooth functions, if that commutes with the classical Laplacian, this one will come back later. And in spectral triple language, so the Laplacian is, of course, a second order operator, not very suitable for spectral triples, at least at first sight. And the Dirac operators that one usually encounters in spectral triple land are square roots of this thing. But there is a spectral triple analog in the sense that if you have such a diffeomorphism and it commutes with the Hodge-de-Ram operator, then that is an isometry. So these structure groups of G spectral triples, they should be thought of as subgroups of the isometry group of the non-commutative manifold. And maybe they can also often be equal to that whole group. So if you want to construct new examples of G spectral triples, then you need to look for such a group.
Sorry, Bram, just a historical question.
Yes.
The first theorem looks to me like a classic, right?
Yeah, this is very.
But who proved the second theorem? Because it seems to be written in our favorite modern language.
I wouldn't know. I would think this is also kind of folklore.
Okay, it's also folklore. Okay.
I mean, the Hodge-de-Ram operator is been around before there were spectral triples, of course. I mean,
okay, of course, yeah.
I would. Can I ask you, Ludwig?
Yeah.
What is U gamma? U sub gamma?
Unitary.
Yeah, but which? I mean, what is this? If this commutes with.
Gamma is some diffeomorphism.
No, it's okay, but U sub gamma is which unitary? I mean, if the unitary U sub gamma commutes with D plus D at all.
Okay, well, you can implement this as a unitary on this.
Okay.
Well, okay, it needs to be a unitary. Actually, this is an important point, so maybe I should be slightly more precise. This gamma should implement a unitary, so that's already one requirement. So preserve the volume form, and then it should also commute with with the Hodge-de-Ram operator. Actually, this is a good point. It will come back right on the next slide.
This is exactly why I asked my question, because I hardly ever seen in classical differential geometry people saying such things. Let this be a unitary commuting with some operator.
They don't have to, of course.
Exactly. This is why I asked who proved it. Okay.
So here is the definition of the abstract isometry group of a spectral triple, which are those unitaries on the Hilbert space that implement automorphisms of the algebra. And I want some smoothness as well. So I want that the conjugation by U preserves the algebra. So that means it implements an algebra homomorphism. But I want to do this on the differential level. So that's why the curly A appears here. And then it should commute with D. So your groups of your newly to be found G spectral triples, they should be represented inside this isometry group, which is a subgroup of the unitaries on H. And so what I will talk to you about today has been what the focus of this project so far has been, to construct new examples of spectral triples on, well, in this case, I will be specializing two Kunz-Krieger algebras, which are graph algebras, that and determine their isometry group, so that you get a restriction of where your structure group can actually map. And then you can start asking questions about principality. And I want to do this in a dynamical context. So because a lot of cross product C-star algebras and also these graph algebras, they arise from dynamical systems. So there is some commutative object in the background, which will allow us to access some geometry. So we'll look at a metric measure space. I will make this slightly more precise. And then I want to look at a collection of self-maps of this space. I would want them to be homeomorphisms, and they need not preserve the metric or measure, but they need to be compatible with it in a precise sense. And then I want to construct spectral triples on cross products. And here I mean, so this on this slide everything is a bit vague. I mean cross products in a broad sense. So I'm not requiring that gamma is a group, even though I called it gamma. Gamma can be a group, of course, but it could also be a semi-group, say generated by one endomorphism. So I also don't require typically that these maps are even invertible, maybe just
and whatever it is, gamma is discrete, right?
Yes, and I want, for this talk, indeed, I don't want to put any topology. Gamma, I want to be a countable and discrete object, yes. For the types of cross products that I will be looking at. Okay, so let's make some of this more precise and motivate some stuff. So if I have a compact Riemannian manifold, then there is a natural metric and there's a volume measure, and these manifolds have the property that the volume of a ball is proportional to the nth power of the radius. And if M is compact, then you can close those measures in by taking a large enough constant. So the radius to the nth more or less controls the volume of a ball. And if you have in general a metric measure space such that for some number n, which doesn't have to be an integer, this type of equality holds for all balls, then we say the space is A-force regular and n is the dimension. But in the examples that we look at, this n doesn't have to be an integer. It can be some fractional dimension. And there are many examples that in some sense are far from manifolds, so boundaries of groups, fractals, totally disconnected spaces. There are many examples of metric measure spaces that are regular in this sense. And sticking to the manifold case, on a manifold we have the Laplace-Beltrami operator on functions. We already encountered it. It can be defined as the divergence of the gradient. It can also be defined in other ways. Mu is again the volume form, and then this delta is an essentially self-adjoint operator on L2 of this manifold. And being the square of a spectral triple operator, it knows stuff about the geometry, as most of us here, I think, know well. So you get that the resolvent is trace class as soon as you take a power higher than half the dimension of M. And this delta, as I already said, commutes with isometries. But commutators with other diffeomorphisms are very often not bounded. And two questions one can ask is, can you make sense of a natural kind of Laplace operator on a metric measure space, by which I mean using only the data of the metric and the measure? And can we say something about, can we construct delta in such a way that commutators with non-isometries are also bounded? And this is important for the types of cross products that one wants to typically consider in NCG. So now there is a little miracle about the Laplacian on Rn, which is that if you take fractional powers of the Laplacian on Rn, then this can be written as an integral operator. So I believe that this kind of equality here holds as soon as alpha is not an integer. And what do we see here? We see that, okay, we have a differential operator, but when we take fractional powers of it, it becomes actually an integral operator, singular and all. I mean, there's all kinds of analysis going on here that we don't want to worry about right now. What's important here is that this expression here uses only the metric on Rn, because the difference of the absolute value here in the denominator is the Euclidean distance, and the measure, the standard measure. And then you can write down this operator, and that is apparently the Laplacian. Of course, it's non-local, which is very different from the actual Laplacian here. There are other descriptions. This operator appears in analysis in many places.
Bram, Ludwig again, but for alpha equals 1, it is just the Laplacian or not?
No, I don't think so. For these integer values, this is not the actual Laplacian.
Okay, thanks.
You'd have to ask the global analyst what happens then. So on a manifold, we can do the same, of course, but we can reverse the process. And here, so Rn is not compact, and we actually get equalities, but there are other analytic problems arising from non-compactness. I don't want to worry about those. So if we have a compact manifold, we can write down this operator. It turns out to be densely defined. You can easily show that it's well defined on say on Lipschitz functions, and it turns out that for alpha between 0 and 1, I write here alpha positive, but I should write alpha between 0 and 1 is more correct. This turns out to be a bounded perturbation of that fractional power of the Laplacian. So it's not exactly equal to it. There is some perturbation term, but it's bounded. And the point I want to make here is that, okay, so up to bounded perturbations, we can write the Laplacian or some power of it intrinsically using only the metric and the measure. And that opens up doing this kind of thing on non-smooth spaces. Also, when alpha is equal to 0, we don't get a power, but we rather get the logarithm. And that is also quite important because the logarithm is such a slow growing function that logarithmic operator has rather remarkable properties. But as said, this delta lower alpha is intrinsic to only the metric measure space structure of the manifold. It commutes with measure preserving isometries, and that is more or less direct from the definition. So if an isometry preserves the metric and the measure, then a simple change of variables trick will show you that this operator is invariant for that. But it also turns out to commute boundedly with multiplication by C1 functions. That's also a rather simple estimate, and also with conformal non-isometric diffeomorphisms. So, but that last statement only holds for the logarithm, not for that only for alpha is 0. For alpha is positive, this of course behaves more like a classical pseudo-differential operator. Okay, so what can we do? We take a metric measure space and we can consider this operator delta alpha. And this is a well-defined, densely defined operator in L2. As soon as we have this alpha's regularity, by which this symbol, I mean the two inequalities. So there's an upper and a lower bound to some powers of the radius. And that is extremely important to make things work. So with my collaborator on this project, Dimitris Gerontogiannis, who's currently a postdoc in Warsaw, it took us actually quite a long time to get this theorem, but it's that is the first part of this work. It's now published in Transactions, so we are happy about that. But I'm also, the paper I'm mentioning there is we focused initially on the alpha is 0 case, because that for NCG is the most important case, but current work in progress also involves the positive alpha case. And I've incorporated some of the statements for that case already because it will come back in the outlook. So we have these operators for each alpha. Alpha can be 0 and it has to be strictly smaller than 1 for it to be densely defined. And you can then write down a Dirichlet form, so standard analysis technology. You get an operator, and it turns out this operator has compact resolvent, and the heat operator, the heat semigroup associated to it, is trace class for large T, and in the logarithmic case, so in the alpha 0 case, there is a positive threshold after which this becomes trace class. And we don't have a full understanding of this threshold yet. If alpha is positive, then we get much better properties. We get that actually the resolvent itself is trace class like on manifolds as soon as T is larger than the dimension over alpha. And in that case, you get very nice, you get a Y law, and you can understand the spectrum in a very good way. The logarithmic case doesn't really have that. For Lipschitz functions, these operators have bounded commutators, but even more remarkably, these commutators are even compact. That was surprising to me. The ordinary Laplacian doesn't have that property. So there, the bounded perturbation will usually destroy this property. And for positive alpha, there you can know even more about these compact operators. So they can also have trace class properties. But this is part of current work in progress. I will not mention that very much now. If we have a measure preserving isometry, then it commutes. I already said that. And if you can make sense of the notion of conformal map on a metric measure space, and then delta 0 will commute boundedly. Delta alpha will not, but delta 0 will commute boundedly with conformal maps. Okay, so this will be the setup to go to the non-commutative case, where I will focus on the Kunst-Krieger algebras. Again, I will assume that most of the audience has some knowledge, but I will quickly recap. So we have a matrix consisting of zeros and ones, usually assumed to be primitive. And then you can associate a universal C-star algebra to it, generated by n elements satisfying these relations here. Okay, so this is a generators and relations description, which is often very useful. There is also another picture which is also often very useful, and that's the groupoid picture. So the groupoid model for the Kunst-Krieger algebras is constructed from an underlying dynamical system. So given this matrix, we can form an infinite sequence space, taking admissible sequences determined by the matrix A. And on that space, we have a shift map, which is a surjective, but usually non-injective local homeomorphism. And this type of dynamical system is often called a subshift finite type. And then you can form the following subset. So you cannot take an ordinary cross product here because this sigma is not an invertible map. So it doesn't generate an action of the group Z, but rather it generates an action of the semi-group of natural numbers. And that's where if you want to take some type of cross product, you have to take a bit more care. Oh, I see a typo here. This omega should also be a sigma. So I want to look at triples X and Y, where X and Y are both in sigma, and N is an integer, and such triples are admissible if there exists some K positive, such that N plus K is also positive. And there's another typo, sigma N plus K of this first point X should be equal to sigma K of Y. And it turns out that one can give this the structure of an étale groupoid. These groupoids are very well studied in the C-star algebra literature, I would say, by now. And they are sometimes referred to as the Diaconou-Renaud groupoids. The groupoid C-star algebra, I will not elaborate on the construction of that object, but you can associate a C-star algebra to a groupoid by completing the space of functions on this set into a C-star algebra, and it turns out to be isomorphic to the Kunst-Krieger algebra OA.
Bram, may I ask you, could you please remind me what is the requirement for a graph to give you Kunst-Krieger algebra and not a general graph C-star algebra? So what are properties of the graph that boil down to being Kunst-Krieger?
I'm not sure if I'm the right person to answer this. I mean, this is just a finite graph without sources and sinks or something?
Yeah, that's exactly what I was thinking, but I'm always confused about it. Okay.
Yeah, I never really think. I think that's true.
Okay.
And that corresponds to the requirement that the matrix has to be primitive, right?
I'm not sure. I mean, if you have a finite graph, in particular, when you have no infinite emitters but this without no sources and no sinks, that's a bit more tricky. I'm always confused about it.
Well, this corresponds to a condition on that there's no row or column with containing only zeros, right?
Oh yeah. Okay.
Like that. Okay.
Yeah,
well, we can look this up.
Yeah.
There are certainly graph algebras that are not Kuhn-Krüger algebras. Okay, so this dynamical system admits a regular metric measure space structure, and that's why we can apply those Laplacian techniques in this context. So there is the usual definition of cylinder sets in this sigma A, which means that if you specify a finite number of letters, so a finite word, then you want to look at all the infinite sequences that start with that particular word. That's called a cylinder set. And if you fix a positive number or a number strictly greater than 1 lambda, then you can define a metric. And the metric is such that the balls for that metric are exactly those cylinder sets. And then, so you don't have to know what everything on this slide is. What I want to convey here is that this metric measure space structure is very closely tied to the dynamical system. So if you know about these things, you can take the maximal per Frobenius eigenvalue of A with it, and there's then an eigenvector associated to it. You can do the same for the transpose, and then you can write down a measure in terms of that data. And again, here the point is only that we start from this primitive matrix, we built a dynamical system, but also from that same data, we get a metric and a measure, and then the resulting metric measure space is Alfors D regular in the sense that I mentioned before. So there is a Laplacian in that setting. And now I'm going to wipe a whole lot of stuff under the rug, but it turns out that you can equip this groupoid GA, so this much bigger set, this one, you can use the metric measure space on sigma to extend this to the layers in the groupoid. And so you can define not really a metric on this groupoid, it will be an extended metric. So you have to decompose the groupoid into pieces, and you have to say, okay, the different pieces are at infinite distance. But this you can sensibly do. This metric will then induce the right topology, and the infinite distance means that it has to be interpreted in this formula as that the denominator is infinite. So this will give you a 0 type expression. But then you can globally write this Laplacian on this groupoid using the same ideas. And this gives you a well-defined and essentially self-adjoint operator. And from that, we can look at the projection onto its kernel. And it also turns out that there is a proper length function on the groupoid. So this goes from the groupoid to, well, in this case, the natural numbers. But this just basically measures how far an element is from the unit space. So it's the analog of a length function on a group where you express how many generators you need minimally to express a certain element. And this is an analog of that, but the precise definition will be somewhat technical, but you get from such a length function, you get also a multiplication operator. And you can assemble all this data in the following way. Now, this will look a bit funny if you have not seen this before, but we take the negative of this Laplacian, and we take the sign operator that we get from the kernel, and that we multiply against this ML. And this defines an odd spectral triple for the Kuhn-Krüger algebra. And the reason to do it in this rather funny looking way is that when you assemble it in this way, you actually get also a non-trivial K-homology class. And the K-homology class of this operator will be Poincare dual in the sense of Kaminker-Putnam to the unit element in K-theory. And you know, in many cases that is non-zero, but also one can actually modify this operator slightly, again, using ideas from this Poincare duality, where you modify this potential operator. So this is also a nice way to think of this operator. It's like, it looks like a Hamiltonian in physics because you have a Laplacian plus a potential. The potential kind of determines the K-homological behavior, which is why it's there. And the Laplacian controls the geometry. That's how I think of this. And so you can generate the entire odd K-homology of a Kunz-Krieger algebra in this way. So these are, in some sense, therefore, at least topologically, an interesting class of spectral triples. So this is a recent result where also Magnus Goffeng from Lund was involved. And okay.
Sorry, Bram, how do you know that this class is non-trivial? How do you determine it?
Well, that uses this Poincare duality. It would take us a bit too far afield to do that. But what you can do, because this PA is the kernel projection, I could have actually added another line here. You can completely factor out the 2p minus 1. And then it gets multiplied by ML plus the Laplacian. That's a strictly positive operator. So that means that 2pa minus 1 is a representative of the bounded transform. So that gives you actually a Fredholm module. So the Fredholm module, the class of the Fredholm module is equal to this 2p minus 1 thing. And once you know that, you can use Poincare duality technology to determine that this has to be dual to the unit element in the K-theory of OA transpose. So in some sense, so very long ago with Magnus Goffeng, we started looking at these spectral triples on Kunz-Krieger algebras, and we understood this type of correspondence, I guess.
And what do you mean by OA transpose?
The transpose matrix also that defines a Kunz-Krieger algebra. And Kaminker-Putnam's duality goes from OA to OAT. So the dual, the Poincare dual algebra is the Kunz-Krieger algebra associated to the transpose matrix. So about 10 years ago with Magnus, we understood that such spectral triples have to somehow look like this, where there is this 2p minus 1 and then times something positive. The something positive we initially built as a more or less artificial thing by just looking at the structure of the groupoid and just doing what we can do. So basically forcing in the spectrum. So the progress here is that this construction is geometric now because it really uses a length function and a Laplacian. So these are new representatives for classes that we already had some representatives for. And I'm arguing that these are the right representatives. Because we can actually determine the isometry group of these spectral triples.
That's great.
There we are. So there is an underlying directed graph associated to A, and the graph automorphisms of that graph are exactly given by the permutations on n elements that commute with the matrix A, and now really as matrices. So this is a subset of the set of permutations on n elements. Now that group, this is a group, it acts by conjugation on n copies of a torus, where you view this torus as diagonal matrices with entries, complex numbers of norm 1, and then you can conjugate by a permutation matrix. You land back in there. So you can form a semi-direct product group consisting of this torus and this odd A. Now, I must say that this odd A could be either very big. So for the Kunz algebras, where the matrix consists of all ones, this odd A is the whole permutation group. But it's not so hard to write down graphs where it's actually just the identity. So this could also be potentially very small. But this torus is always there. And this group acts on the generators of OA, so the SIs, by just permuting the indices of the i's, and because of these relations, that's compatible with the Kunz-Krieger relations. And the Tn acts on each generator like the gauge action. So the familiar gauge action is a circle action. It acts on each generator by multiplication by an element from the unit complex numbers. Now we make the n-torus act by acting on a particular generator with a particular element. So it depends which generator you act on, which complex number you will see. I'm actually curious towards this audience whether, I mean, this torus action on the Kunz-Krieger algebra it's fairly natural. I haven't seen it used a lot. So the gauge action, which corresponds to the diagonal here, is used a lot, but this n-torus, I haven't seen it been exploited as acting very much.
Well, if you look at quantum spheres, which are of course graph C-star algebras, then the diagonal action will simply give you projective spaces, Waxman-Soberman projective spaces. But here you can go funny and change this action and do other things.
Yeah.
So then there you go. You can also construct lens spaces this way and stuff like this. So yeah, it is a pretty natural thing, and I understand that your unitary numbers of the torus, that they act when you say generators, you mean these partial isometries. You never.
Yeah, I mean the SIs and the SJs, and the relations are preserved by such an action. Because they involve only SS star and S star S, and then this goes. So you have this freedom. It's just there, and I'm sure this has been observed before. But for us, it popped up sort of naturally because we can prove that the abstract isometry group of these spectral triples is exactly equal to this rather small group, which encodes the symmetries of the graph and then this action on the generators. And so it's a subset of the unitary group. And so we were kind of happy with this result because if you want a geometric spectral triple should not have too big an isometry group. Maybe also not too small, but as I said, this odd A can be very small and it will correspond somehow to the homogeneity of your space. So the Kunz algebras correspond to a very symmetric situation, like a homogeneous space in harmonic analysis or something. And then you get this full permutation group, but it could also be very small. But the torus is always there. And so now that you have this isometry group, you can ask questions, and that's where some work in progress should be mentioned. So now one can ask about principality and factorization questions for Kunz-Krieger algebras. As I said, the work I just presented is fairly recent, so we have not gotten into this question. Compact quantum metric space structures using these Laplacians, and here I write stay tuned because this is a work in progress that is almost finished. Will hopefully be out within the next 2 months. But because it's not out yet, I refrained from saying a lot about it. And then, of course, there is a pattern here where if you have a metric, if you have a groupoid with a metric measure space structure, there is a Laplacian, maybe there is also a length function. Can you do this? Can you do this type of spectral triple construction in general? And will the isometry group be computable? For certain Kleinian groups, cross products by limit sets and so on, the answer is yes, but this is also still some work in progress. And then another direction as part of the equivariant spectral triple work package that I have not mentioned at all here is equivariant Levi-Civita connections on quantum flag manifolds, which is where Branimir Kacic, the collaborator on this project in New Brunswick, will be involved. But this is still
you mean New Brunswick?
New Brunswick, yeah.
Yeah, there's also Old Brunswick
Did I say
in Germany.
Okay. Sorry, but this this is still waiting to be explored. So I just wanted to mention it here as this is a report meeting, but this was the end of my talk, and I wish you all happy seasonal greetings, as one says.
Thank you very much, Bram. I mean, this was perfect. You spoke for exactly 45 minutes and 2 seconds. I mean, how do you get such a precision? No, that was a masterpiece, and it's a very beautiful presentation.
A lot of
And
experience.
brilliant. I mean, and this was a very beautiful report. Now, we still have 5 minutes for questions before the next talk. I already asked many questions, so please, guys, go ahead with your questions.
Well, I know that recently Dimitri spoke in the Warsaw online
Yes,
about
yes.
a lot of this work, so maybe
Yes,
people
but
have
Dimitri is not here.
No. But I mean, if people have seen his talk, they may not have
Okay.
any questions now. I don't know.
Okay, Tomek has a question.
Yes.
My question is about some strange similarity between this action of on this torus, diagonal torus.
Yeah.
So usually such action comes from some action of a Weil group on a maximal torus of a Lie group, corresponding to some root systems of some simple Lie groups. Okay. Is there any connection between this graph picture and this Dynkin diagram in this context?
I don't know the answer, but I find this a very interesting remark, because I was asking myself when we discovered this torus showed up, I have been wondering, so since last spring, it's not been for very long, like what the meaning of this is, because it seems to be some inherently non-commutative thing, even though it's sort of the simple part of this Lie group. It's also it only acts on the algebra. It's not implemented on the space. So I will just take your remark at face value and think more about this, because I can't. This might be a way in to interpret what this means, but I wouldn't dare to say that this is true. But this is a very interesting remark.